Hi, my name is Marco Lisi. I work for the European Space Agency in the plant in Holland, ESTEC. I'm presently involved I work for the Navigation Directorate, and I'm involved in the development of the two navigation programs of the European Union and of the European Space Agencies, EGNOS and Galileo. But today I will not speak about navigation, rather I will give you an introduction to antennas for space applications. Let me say something about the objectives of the course. I want to explain to you what the antennas in general are, why they are so important in our everyday life, and in particular why they are so especially key in space applications, in satellite applications. I will explain some fundamental concepts and definitions about antennas. I will suggest some very quick and dirty methods to evaluate the performance of an antenna, with almost no mathematics involved and just a few formulas, such that you can use them to evaluate and understand the problem related to the design of an antenna. And then finally I will offer you a synthetic overview of antenna technologies and of some key configurations for onboard satellite applications. So I have divided the course in 3 lessons. The first lesson, I will start looking at the etymology of the word antenna. I will explain what the electromagnetic waves and the electromagnetic spectrum is. I will remind you about the concepts such as wavelength and period. I will present the antenna as a transducer between conducted and radiated electromagnetic waves. I will speak about the reciprocity principle. I will define the antenna directivity and explain what the antenna beam patterns are. I will define antenna polarization. I will, very important, show how to calculate the directivity and gain of an antenna. I will present the antenna beam width and the concept of gain area product. And then I will just define the concept of antenna temperature. So let's move on about presenting the importance of antennas. Antennas are really everywhere in our life. They are used to receive the TV programs. They are used in our radios. They are used in many applications, in airports, to communicate with airplanes. There are a lot of military applications, but also many radars, even civil radars, are based on sometimes very large antennas. And we should not forget that antennas are also in our pockets, because they are in all our smartphones, in fact in all our computers. Our computers communicate with Wi-Fi by means of antennas, and our smartphone connected to the cellular network by way of antennas. So antennas are really very important, but they are also very, very, very important in satellite communications. And in this picture I show a very nice view of the biggest, probably the biggest teleport, satellite teleport in Europe and maybe in the world, that is in Fucino in Italy, is the teleport of Telespazio, where there are hundreds, literally hundreds of antennas. Some of the antennas are huge antennas, reflectors of up to 30 or 40 meters in diameter. And those are the ears that would allow the companies, let's say, involved to communicate with satellite in space. Let's also define, because it might be important historically, to understand the etymology of the word antenna. The term antenna is used in several fields. In fact, we call antenna the sensors used by insects to communicate and to orient themselves while moving on ground, for instance, or even while flying. But antennas are also used for our use in electromagnetic communications. But actually the origin of the word antenna is probably from Greek or Indo-European word, but the meaning of it is really the pole used to raise sails in a ship. So it's a nautical term, in fact. And why was this term used eventually for the applications related to radios and electromagnetic wave transmission? Because of an Italian guy, inventor, Guglielmo Marconi, who is the father of radio communications. In 1895, he started making some tests about the use of wireless systems to communicate through the way of Morse coding between sites that were every time more distant. And in fact, in that year, 1895, he made the first real transmission using electromagnetic waves. And this guy, he was 19 at that time, had read some years before about the experiments of Heinrich Hertz that were proving that electromagnetic waves were exactly of the same nature of light. Nobody knew about electromagnetic waves. Nobody thought that there were waves working at the present radio frequencies. So he was proving with this experiment. He never thought about using these electromagnetic waves for communications. Marconi had this intuition of using them for communication. And he was also an expert he was fond of sailing, and he knew about the nautical terms. So when he put his antennas, but he didn't know that he had not named yet them antennas, these long wires to communicate to long distances the radio waves, he thought about calling this aerial, in fact the aerial wire, antennas as similar to the poles that are used in a sail ship to raise sails. So this is, since in Italian these poles are called antennas, then the term antenna, little by little, was used as a term to indicate, in fact, the transducer, the interface of any radio communication system with the free space. So this is the etymology of the word antenna. But what are antennas, in fact? What do they do? Antenna radiates electromagnetic waves. So they are, first of all, the way through which you can transform an RF signal into something that propagates in space. You can also think, well, first of all, the electromagnetic waves are part of a very large electromagnetic spectrum. So the radio frequencies that we use, for instance, for our smartphones and also in our satellites, are just part of a very large electromagnetic spectrum that goes from the very long radio waves, getting down, in fact, to DC, to the continuous wave that we use in our batteries, just to make an example, up to the very short wavelength electromagnetic waves, such as the gamma rays. And in between there are all the waves we are used to. So we go from the FM radio waves that we use to listen to music in our radio. We go to the microwave frequencies that are used especially in satellite communications, also in ground communications. And then moving up, we go to infrared frequencies, and we eventually get to the visible spectrum. The visible spectrum is the electromagnetic waves that we see through our eyes. Our eyes are, if you want, antennas that are sensitive to the visible spectrum. And then moving up, you go to ultraviolet frequencies that are those invisible frequencies that are responsible for our sunburns. And then up again, we get to X-rays and gamma rays. So we, as human bodies, are in fact antennas. We are visible, so we are radiating in the visible spectrum, but being also rather warm, we radiate in the infrared spectrum. So everything in our life, in fact, radiates something, and it is, if you want, an antenna. But when we speak about antennas, we think of something that is able to make an electromagnetic wave propagate. The electromagnetic wave is a a wave that is composed, that can be decomposed in two fields, the electrical and magnetic fields. Those two fields in a propagating electromagnetic wave are always orthogonal, one to each other, and they are orthogonal to the propagation to the direction of propagation. There are some definitions related to waves that are very fundamental. One is the wavelength. The wavelength is, if you look at the electromagnetic wave in terms of amplitude over distance of propagation, then we see that the wave is a sort of sinus and repeats itself. The distance between two peaks or two nulls of the wave is called the wavelength. And the wavelength can be expressed as the multiplication between the speed of light and the period. What is the period of the electromagnetic wave? If you look at it now at one point in space, but over time, then we see that over time, again, the amplitude of the electromagnetic wave, electric or magnetic field, repeats itself following a sinusoidal type of evolution, and the distance between two peaks over time or two nulls over time is the period. The inverse of the period is the frequency. So the lambda wavelength is the multiplication of the speed of light being 3 by 10 to 8 meters per second. So in terms of kilometers per second, it's 300,000, approximately 300,000 kilometers per second, multiplied by the period in seconds, or conversely can also be expressed as the ratio, the speed of light over f being expressed in hertz. That is the dimension used to express frequencies. There is also a quick and dirty formula to get the wavelength of an electromagnetic wave. When we deal with microwave frequencies, the lambda wavelength in meters is equal to the ratio 0.3 over f expressed this time in gigahertz. So it's a very simple way to get the lambda meter, for instance, of a reflector antenna, we'll see later on, knowing the frequency of the electromagnetic wave, the operating frequencies we are interested in. What is then an antenna? We said an antenna is somehow a sort of interface. The interface in a communication system, for instance, a satellite transponder, we have something that generates a signal, an RF signal at a certain frequency, it amplifies it, for instance, with maybe a power amplifier, and then this signal is transmitted through a transmission line. This transmission line doesn't interface directly to the open space. It keeps the signal confined. This transmission line can be a standard cable, the cable that we use also for connecting our TV to an external antenna, or can be at higher frequency waveguide. That is another type of transmission line. This transmission line keep the RF signal confined. We need then to radiate, so we need to interface with space. We need to create, in fact, this propagating wave that would go as far as it is possible, of course, decreasing its intensity, its power density with distance. So the antenna can be seen as a transition between the transmission line and free space. So this is what really antennas are, a sort of interface, sort of transducers between a world of confined and guided waves into a world of free propagating plane waves, electromagnetic waves. So one very important principle about antennas is the principle of reciprocity. The principle of reciprocity states that receive and transmit properties of an antenna are identical. We just saw before that antennas can be seen as a transducer from a guided wave to a propagating plane wave, and vice versa, from a plane wave to, so we can distinguish between transmitting and receiving antennas. But if the antenna is made of reciprocal components, and we will define them later on, let's say in practical terms, all passive antennas, they are completely reciprocal in the sense that the same antenna can be used with the same properties, with the same characteristics, either to transmit or to receive. And this is also very important, also because many times in designing and then eventually testing an antenna, it's completely indifferent whether we design it for receive or transmit. In fact, the antenna is the same. Also for testing purposes, we can, depending on our convenience, to decide to test the antenna in receive mode or transmit mode. As I anticipated, there are some type of antennas that are not, for which the principle of reciprocity doesn't apply. Those are, for instance, the active antennas. Active antennas, we'll see them in lesson 3, are antennas that are embedding active components in receive low noise amplifiers, for instance, in transmit power amplifiers. And of course, in this case, if you consider the antenna the complete subsystem with not only with the passive components but also with active components, reciprocity doesn't apply. An active receiving antenna cannot operate as an active transmitting antenna. You need different type of components. But apart from this particular case, that is also very important, but the normal antennas we consider in satellites, also in most of our ground applications, are such that the principle of reciprocity applies. It's very important. Now let's speak about a very important concept, that is the concept of antenna directivity. I have tried in this slide to explain this concept in very simple terms. Usually, to define directivity, you have to introduce the concept of isotropic antenna. But what is an isotropic antenna? By the way, it's a pure mathematical concept which doesn't exist in nature. An isotropic antenna is an antenna that radiates in the same way in all directions of space. So it's an antenna that if you put it in a sphere, or whichever is the radius of the sphere, and you go sampling the power density received by the antenna over the surface of the sphere, this power density will be the same. So let's make a simpler example. Let's suppose that we have a sphere. Let's imagine as an approximation a room, and in the center of the room I put a lamp, an electric bulb. In the first approximation, I can think that this bulb is illuminating the room, or let's suppose the sphere, in the same way. So wherever I go, I find the same light intensity. Let's now imagine that I take a mirror and I put it behind the bulb. It's obvious that there will be an area of the room or the sphere, if we want to get to the mathematical example, that is more illuminated because the mirror will converge the light waves in one direction. This is, in fact, the concept of directivity. So one very important concept to understand is that antennas are not creating power. Antennas are passive components. You do not feed any DC power into an antenna unless it is an active antenna, but this is a very special case, we mentioned it before. A passive antenna, it cannot create power. The conservation of energy applies, it's a fundamental law of physics. So this means that when you say the antenna gain, the gain or directivity, we'll define the directivity versus gain, is not something to do with the real creation of energy. The antenna is not increasing the energy. The antenna is focusing the energy into a certain direction. And this is what we want, because we want, in fact, for instance, in a satellite communication, to converge the RF energy into the direction of the link to our, for instance, ground station. Antenna is not creating anything. It's different from an amplifier, for instance, even a sound amplifier. In a sound amplifier, you use the power supply to actually increase the power of a signal, of an input signal. There you convert DC power into the sound, let's say, low frequency power, but you are not again going against the laws of physics, because you need a power amplifier connected to the electric network. In the antenna, you do not have, unless it is an active antenna, you do not have any connection to any source of power, so you cannot increase the energy, you cannot increase the power, you just focus it. So this is really a very important concept of directivity. So the definition of directivity now being a bit more formal, we speak of directive gain. We'll see that directivity in fact is the maximum value of this directive gain. Directive gain of an antenna is the power density the antenna radiates in one specific direction. So in fact you can define the directive gain as a function of the angle from which you look into the antenna. You'll see that it depends on two angles, theta and phi usually, defined. And this density, this power density is compared to the power density radiated by this ideal isotropic radiator, which doesn't exist. It's just a mathematical approximation, if you want, idea, concept. This isotropic radiator, in fact, is the one that would radiate uniformly in all directions. The ratio of these two gives the directive gain of the antenna. It depends on the angle, depending on the direction from which you look into the antenna, starting from a sphere of a radius undefined, then you can define this directive gain. The directive gain, D, is a function of the two angles theta and phi, so it depends on the direction. The maximum value, if you look at the complete space, the full sphere surrounding the antenna, the maximum value of this directive gain is called directivity. Directivity is usually expressed in terms of dBs. It's a convenient way also because not only for calculations, you know that it's very easy to make calculations with dBs because multiplication converts into additions and ratios converts into subtractions, but it's also convenient because usually the gain of an antenna is expressed in very large numbers, and dBs help reducing these large numbers into numbers that are more manageable. So the definition of directivity in dBs is the 10 times logarithm by base 10 of the ratio we defined before, so the ratio between the power density actually radiated by the antenna we are considering in one specific direction over the power density of the ideal isotropic antenna. When we speak of directive gain, we usually add to the dBs of the directive gain the subscript I to remind ourselves that the reference in our ratio is the isotropic antenna. So we call of directivity in dBIs. As I said, we can usefully define the direction we are considering while looking at the directive gain of an antenna, adopting the definition of angles, azimuth and elevation that are in fact astronomical terms. When you want to define the position of the sun, of a star, as compared to your position on the Earth, you consider the zenith as the direction moving above your head, the nadir as the opposite vector going in the direction opposite to your head, and then you can define an angle that is just around you over the horizon, that is the azimuth, and an angle that is in fact measuring the elevation of this star or the direction of propagation of the antenna moving from the horizon up to the zenith. So the azimuth angle is a 360 degrees angle, and the elevation angle, if you consider the full space, is plus or minus 90 degrees from horizon up to the zenith and from horizon up to the nadir. So then we can, using this definition of angles, we can also describe in fact the directive gain of an antenna, expressing it in terms of patterns. The most complete pattern, if you want, is the 3D pattern. So you can, in this slide, you see that you can really represent how the antenna is propagating in the various directions. Of course, this pattern expresses the amplitude. The amplitude can be normalized to 1 to 0 dBs. In fact, 1 would be expressed in dBs, 0 dB or dBis. Another convenient way to represent the patterns of an antenna is to take cuts of this 3D representation, and then you can again show these two-dimensional cuts either in a polar form, and this is the picture on the bottom left side of the slide, or in rectangular cuts. They are completely equivalent, so depending on the cases you might prefer to use one or the other, but the information that is conveyed is the same. The two-dimensional cuts are usually more useful than the 3D pattern to take in fact measurement as a result of the testing of an antenna. The 3D pattern gives you an idea, it's a very representative way to give an idea of the characteristics of the antenna. But in terms of measurements, in fact, the polar cuts or rectangular cuts are more useful and are more normally adopted. Let's look, for instance, at the two-dimensional polar cut, and let's see how we can derive from it some important information about the antenna. So we can define a main lobe. The main lobe is the lobe of the antenna that is in fact conveying the most of the energy, is where the directivity of the antenna is concentrated. The peak of this main lobe, as we defined before, is the actual directivity of the antenna, directivity being the maximum value of the directive gain. Then we can define another two important points in the lobe. This is in a two-dimensional view. These points are the points where the power is half of the power density, is half of the value you get onto the maximum of the lobe. Those 2 points, you can define right, of course, and left point, are the so-called half power point. The distance, the angular distance between these 2 points, the 2 half power points, defines the so-called half power beamwidth of the antenna. This is a very important value in an antenna. In fact, we'll see later that there is a relation between directivity and half power beamwidth. And it's also important because it's another way to look at the goodness of the antenna in terms of capability of focusing the energy into a certain direction. It's obvious that a small half power beamwidth represents a more directive antenna. There are, of course, many advantages in having small half power beamwidths. There are also some disadvantages. For instance, I can anticipate, it's more difficult to point exactly the antenna into the direction of we want to create our link, for instance, to a satellite or from a satellite to the Earth. If the beamwidth is small, you have to be very accurate, otherwise you risk not to direct the peak of the antenna in the right direction.